I just calibrated a network of radar sites using machine learning to precisely determine where space objects are. Currently, we use ground stations that have radars that send radio waves to space, and those radio waves bounce back, revealing information regarding where space objects even are. Now, I made a machine learning model that can take that same information, but from multiple radar sites, to precisely determine where the space object even is. Let's take a look at it. Here we have the machine learning model itself, where this is the input, azimuth, elevation, and range from 3 different radar sites, and we can make a prediction using the machine learning model, which will output us calibrated AER data. So if we run this, we can see this predicted azimuth, elevation, and range, which gives us information regarding where the satellite is, but it takes into account multiple radar sites this time instead of just one, and makes up for any imperfections within these radar sites, giving us more precise information on the radar sites rather than just relying on one radar site. Now, it is really hard to calibrate these radar sites normally because there are many parameters that go into account, such as the frequency, sensitivity, or field of view of the radar site, and there's also other factors like Earth's curvature that can affect the data we get from each radar site. But this is essentially just a regression problem. How can you take input from radar site 1, 2, and 3 and make it as close as possible to the actual value? So then the question becomes, where did you get the data from? I simulated the entire data set using SDK by AGI, not artificial general intelligence. I set up 3 ground stations across America in the simulation and simulated the Starlink satellite to gather AER data, specifically data regarding the position of the satellite from these 3 ground stations and their overlapping region, and fed that information into the CNN to train the machine learning model. Wait, but why did you not just use a regression model? Well, you can also use the CNN for regression tasks. If you swap the classification layer with a single unit dense layer, you can also use CNNs for regression. A single neuron in a dense layer will allow the CNN to output only one value based off of all the combined features. Lastly, if you replace the loss function with mean squared error or something along the lines of that, you can create this perfect regression environment with a CNN. Wait, but why do we even need this? Satellites have 3 main orbits: low Earth orbit, medium Earth orbit, and geostationary. Now, low Earth orbit has a lot of applications like Earth observation and communication. Because of all these applications, the number of satellites in low Earth orbit are ever increasing. It's almost an exponential increase in the number of satellites. This increase in satellites is increasing the probability of collision between spacecrafts and space debris over time. This is leading to a phenomenon called Kessler Syndrome. In 2009, the Iridium-33 satellite and the Cosmos 2251 spacecraft collided, resulting in more than 1,400 trackable debris larger than 10 centimeters, and this doesn't even include the millions of debris that weren't trackable. More collisions like these can lead to more debris, and those debris can lead to even more collisions, creating this domino effect of collisions over time, which is better known as Kessler Syndrome. If this pattern continues over time, it will become impossible to send more spacecrafts up into Earth's orbit. Therefore, it is crucial to mitigate Kessler Syndrome starting now, which is what my project aims to do by precisely tracking space objects, helping us avoid collisions over time. If you found this project interesting, subscribe to me on YouTube, make sure to follow me on Twitter, and definitely check out my Substack for monthly updates on the project I build. Until then, I'll see you next time.